Alright, Chapter 2, Nitrous Oxide Reduction in Large Two-Stroke Diesel Engine. Of the main combustion that they have a large commercial use of the diesel engine that provide with great technical channels to achieve the significant nitric oxide reduction. Two general approaches use the nitric oxide emission from the modification engine combustion process with view of the nitric oxide specified with the nitric oxide, nitric dioxide, or generated B with and or treatment exhaust gases to destroy the nitrous oxide specified species generated to prevent with the emission atmosphere with the diesel engine. Lean burns skidiometrically fuel lean with a catalytic reactors with the spark ignition. Gasoline engine is to reduce the nitric oxide hydrocarbon emission with required with a near stoichiometric combustion, not effective with reducing concentration of the same pollutant, especially with the diesel exhaust. Further, diesel engines operate with a higher compression ratio for the gas engine with the combustion in them proceeds according to the complex heterogeneous diffusion process opposed to the simpler with the easier to control with homogeneous flame propagation characterization. Gasoline engine combustion and the higher combustion ratio of the diesel engine leave with the greater efficiency for the diffused controlled combustion permits for the operation of higher pressure without the occurrence of the destructive knocking. However, both of these factors lead to higher combustion temperatures and increase the nitric oxide production of the diesel engine. Most of the work reducing the nitric oxide emission for the diesel engine has been smaller for the size of the engine. Little research has been carried out with the engines larger for the EMD 645 as complex for the combustion with increase the one's ability to control the process decreases. Engine size progress with the nitric oxide emission reduction with the larger engines have been comparable to slow, with however the characterization funnel process for the diesel engine improved as a result with the control of the nitric oxide emission with the large and small engine may improve with the Navy official with the Navy Naval Research sponsoring fundamental research is reference 2.1, 2.2, and 2.3 with the control of the nitric oxide emission larger engine with the boat and ship operations. Those results could also be defined with the application of use engines. However, the practical application research was successful several years for the future. Further complication EMD 645 engines, as they are two-stroke engines with reduced number of engine parameters variable to controlling alternating internal engine process proposed with nitric oxide reduction. For the most nitric oxide reduction for the diesel engine has been those of the four-stroke design. Therefore, quantity of the engine research to draw on reducing nitric oxide emission for the EMD 645 is limited. 2.1 exhaust gas treatment that provides one option and signified with the reducing nitric oxide emissions from the diesel engine, though with additional equipment and chemicals required for the implementation working against for the using of the two-stroke approach for the variable commercially other are being developed the variable commercial with the chemical reduction either with a catalyst or selective with catalytic reduction or without catalyst selective with non-catalytic reduction. The reductions are usually ammonia related compounds such as urea. Other identification uses criteria with the development of the appropriate catalyst, major technical problem development, even select catalytic reactive select catalytic reduction approach, selective with non-catalytic reduction. Requires no catalyst or other chemical routes. Temperature for the destruction of the nitric oxide must be with the general flow paths for the two approach. Contrast in Figure 2.1. Ammonia has been chemical at most speed with the nitric oxide reduction. Recent years have seen the development of the related chemical with the urea and cyanuric acid. Ammonia have been used with selective with non-catalytic reduction, selective with catalytic reduction processes, but the temperature window in their application selective with non-catalytic reduction is too high to be useful with the diesel exhaust. The use of the urea and selective with catalytic reduction process, rather recent development, other significant advantage over the ammonia selective with catalytic reduction. Urea provides the least nitric oxide reduction. Selective with collective reduction of ammonia provides above both greater than 90%. But without burden being either hazard, chemical, environmental threat. With the use of the selective catalytic reduction urea, developing urea currently available in the European supply of the cyanuric acid has been used in selective non-catalytic reduction, non-catalytic process. Major claim is that with the most effective either of the ammonia, urea, low temperature characteristic diesel exhaust. Part 2.2 Nitric oxide reduction of the EMD 645 dual fuel engine. Some of the efforts done to take the natural gas two-stroke diesel engine for the interfused engine generator program summary with the table 2.1 first line for its operating data with the current use EMD 645 engine baseline with a comparison remaining cause for the engine, same locomotive type of the engines here with the EMD 567, 645, and 710. Cylinder displacement cubic engine with the diesel Detroit diesel 92 with the truck size engine with the fuel type with the dual fuel or natural gas changing in cylinder for the natural gas described in either earlier or later than the compression stroke. For the early injection, low injection pressures 100 to 300 psi can be used. Airflow mixing pattern cylinder produce cylinder through the producing nearly homogeneous fuel air mixture prior to the ignition. Later cycle injection, much higher pressures than greater than 3,000 psi is required as the pre-mixing fuel air not achieved the prior to ignition. Diesel type fuel combustion takes place. Ignition natural gas charge both of these areas with injection pilot quantity with diesel fuel 4 to 7% of the amount of the required full diesel operation into the cylinder at a time ignition. Nitric oxide reduction is achieved with the EI. Early injection nitric oxide reduction is more difficult to achieve than late cycle injection. Anticipated advantage of late cycle injection: creep the engine thermal efficiency, higher compression ratio, diesel cycle will be used to avoid for combustion, not at the limit of the power production. Auto cycle with a homogeneous combustion engine. The disadvantage of the low cycle injection are the technical problem, high cost, providing natural gas temperatures greater than 300,000 psi with difficulty achieving and reducing nitric oxide emission. Higher pressure, higher temperature combustion, environmental advantage, reduced fuel costs due to the use of the natural gas rather than diesel fuel provided with both approaches. The date of Case 1 was obtained in 1982 with the locomotive engine fuel from the compression natural gas cylinders carried over the railroad flat car. Reference 2.4 measured limitations due to the testing operation reduction 20-30% with available engine power with the cause for the onset of the combustion knocking. In Case 2 of the Department of Energy sponsored a single cylinder engine test for the determined to improve the engine thermal efficiency. Power production could be obtained with the diesel type late cycle injection combustion process with the diesel fuel operation. Substantial progress was made within these tests. The engine efficiency exhaust emission objectives were not achieved. The DD92 spark ignition truck size engine. Case 3 has significantly different requirements than those of the large locomotive engines, and manufacturer discontinued after several years of production. Case 4 was undertaken by some of the parties involved with the Case 1. Several changes included with the turbocharging rather than positive displacement compressor for the charging air compression, changing the piston crown designed to improve the fuel air mixture to reduce the compression of 14.5 to 12.8 from alternating head configuration to allow the emission of the natural gas into the chamber with electronic rather than mechanical controls, and incorporating additional air cooling with the engine, modifying with the control of the injector rack, incorporating the single bank engine idling to reduce the emission, improve the engine C efficient, refer to figure 2.7. Results achieved sufficiently to convince the Burlington and Northern Railway to install the retrofit package designed especially for the EMD 645 engine into two tandem locomotive with coal line operations between Montana and Wisconsin. Liquid natural gas was used as the fuel. The separate liquid natural gas fuel car was constructed to provide fuel. Liquid natural gas refueling station was round trip and provided with Minnesota. The performance, reliability, emission reduction technology demonstrated in a program that continued over 2 years. Technology represented with the demonstrated with the 2 tests appeared only with the engine related to retrofitted technology available to achieve the significant nitric oxide reduction in the EMD 645 engine. Last entry of the Table 2, the development test had been underway with the Southwest Research Institute with the development of late high-pressure injection of natural gas. Data regarding performance, emissions, costs, and reliability of the technology have not been yet published. 2.3 further reduction of the nitric oxide emission. Although 70% of the reduction of the nitric oxide demonstrated a result in the Case 4, the important step forward for the nitric oxide reductions appear available with some additional modification of the dual fuel EMD 645 is centered on the use of the pre-ignition chamber to separate the diesel engine igniters. Result presented in this table show that the nitric oxide with the dual fuel injection reduced to the level of 1.0 grams horsepower per hour. Required pilot fuel with the reduced to about 1%, although the use of the pre-chambered engine, familiar concept with the use of the dual fuel engine, limited significant advantage not widely explored. In the case shown with the Wartilsa, somewhat complex multi-fuel application requiring higher pressure injections, it would be useful for the Navy to use units copper Bessemer. Case 2 through 5 can conduct started with the objective of improving the operation of large spark ignited natural gas engine. Result of the major improvement of the dual fuel engine is as well. Copper Bessemer engines were all 4-stroke units, Fairbanks, Morse, and achieved the results similar to those of Copper Bessemer with 900 RPMs 2-stroke, opposed to a piston engine plain view with the injector arrangement of natural gas diesel pre-chamber injectors. Fairbanks, Morse application shown figure 2-3 with the engine operating a diesel mode with the diesel injectors with the natural gas mode, a single low pressure gas injector used along with a diesel fire pre-ignition chamber. Figure 2-4 shows Fairbanks Morse data for the 4 modes of the engine operation: standard diesel, standard dual fuel, spark ignition, enviro design, pre-chamber. Numbers which engine ran region over the figure with the number of the data points defined in the region: nitric oxide emission, thermal efficiency, brake, specific fuel consumption, significantly superior to the environmental design, pre-chamber parameters affecting the reliability, effectiveness, achieving ignition, emission, minimum pilot fuel, is shown figure 2-5, reference 2-8. Combustion pre-chambers can also be used in dual fuel engines to further lower nitric oxide, hydrocarbon, carbon dioxide, monoxide, particulate emissions, improve the engine thermal efficiency, require diesel pilot fuel for both 2- and 4-stroke dual fuel engines. This technology is now available to apply with the 645 and AMD to achieve further important improvement in exhaust emission, thermal efficiency, dual fuel operations. Such word efforts will require modest extension of existing dual fuel technology, low pressure injection, also demonstrated Burlington Northern Railroad locomotive, the Navy Museum. Successful demonstration dual fuel AMD 645 pilot engine was to bring Navy stationary dual fuel units level of nitric oxide required most restrictive emission regulation contrary to the engines. Alright, this shows the heat extractions and exhaust gas combustion gases at 1500 2000 degrees Fahrenheit. The ammonia injection, selected non-reduction heat exhaust gas combustion at 680 degrees, ammonia injection catalyst bed. Standard dual fuel engine, nitric oxide grams per horsepower hour, dual fuel pilot, pre-chamber spark ignition, BSFC, pre-chamber with pilot injector, diesel injection nozzles, gas valve, standard diesel, enviro diesel, spark ignition, nitric oxide grams horsepower hour, BFCCS, pilot fuel injector, NG, natural gas injector head, pre-chamber, main combustion chamber, piston, volume, orifice, or shade, location, orientation, quality, FA, pre-chambers, diesel injector. Table 2 in nitric oxide reduction technology related to EMD 645. Table 2 rather nitric oxide reduction using pre-ignition chambers. Chapter 3 elements of the ECI EMD dual fuel conversion.